So I'm expecting some perfection here. Tomorrow's our first attempt to kind of cash in and see if you guys are acclimating to this. So did we get further? Did we of course draw in what we know about one of the forces? I don't know which one you drew next, but it would make more sense for you to draw the one that's at an angle next. You see, you have no sense of scale for the one to the right, but the one that's at an angle is the only thing that's pulling up on the box. That gives you a sense of scale, because whatever amount you have pulling downwards, the one that's pulling at an angle is the only one providing an upwards force. So your sense of scale needs to be set based on the weight, but the one at an angle is the only one that can balance the weight. So it should have been the next one that you drew to get the sense of scale correct. I labeled this one T2. And then your one to the right has to balance how much the one to the left is going to the left. So something like that. Now from here you had to draw in a coordinate system. Our system is not accelerating, so an appropriate coordinate system is one in which I think we get as many vectors as possible to be aligned. This is our angle theta. You should know that because of alternate interior angles. Knowing where to put your angle is going to be something you will have to become good at. And you all pass geometry, so I have high expectations. But that also means that you've taken and broken this up into its components correctly, with this one being T2 cosine theta, and this one T2 sine theta. I have no intention of doing trig anymore for you. You can do your own trig. This isn't the end. This gets us to step 4. Step 5 is to take Newton's law and apply them. Add up all the forces in the x direction, taking into account the direction, and set them equal to 0. So that's going to be T1 minus T2 cosine theta equals 0. Net force in the y direction also equals 0. So T2 sine theta minus weight equals 0. Again, this is what I'm expecting tomorrow, all the way to here. Now, there's a reason we're doing this. This tells us how much force the cable has to withstand, and maybe helps us decide what angle we should make the cable. Right now, it should be pretty clear to you that the cable, at least one of them, has to withstand more than the weight of the object. You might wonder, why would you just not hang it from the string? That would be just the weight of the object. We use 2 supports to hold it in place, so if it's windy, it's not blowing all over the place. But that costs you something. Apparently, it costs you force. And this angle is going to make a big difference, right? The shallower that angle is going to be, the smaller the sine of that angle is going to be, and that's going to need to make the tension in the cable much higher. But you should be able to get an expression for both of these tensions. Like, what does T1 equal? Don't tell me it equals T2 cosine theta. Put it in terms of the weight. The one thing that we would know would be the weight of the sine. Can you do that? You should be able to. You're all capable math students. Mathletes, the lot of you. Work it out. If it were me, I would consider that T2 sine theta equals weight, while T2 cosine theta, not equals 0, equals weight. Well, T2 cosine theta equals T1. I'm writing them like this because whenever you have something that's sine and cosine, which will happen a lot when you break a vector up into its components, you can divide those two and get tangent on the left and cancel out one of the forces right away, giving you a much faster way to figuring out how these variables are related. You can do substitution as well, but you don't have much time on the exam. So T1 is weight divided by tangent theta. Remember, the point is to tell us something about the system. This procedure gets us to a place where we get information about the forces. It's what we do next that matters. I'm testing up to this point tomorrow. Let's move on. Example number 6. I'm sorry, example number 5. A wagon is being pulled on by a child who uses a rope connected to the wagon to pull it. The wagon is being pulled to the right with a constant velocity. Please give me a relationship that I could use to figure things out about the wagon. Okay? I want the whole thing. This is example number 5. Being that it's early release today, we have limited time. So when I look at this, first thing I want to mention is that, all right, constant velocity, that suggests a net force equal to 0 problem. Next, take my object. The object is the wagon, reduce it down to a dot, and begin to draw the forces that are acting on it. I will go in order. I believe there's a conservative force acting on it. Gravity, pulling downwards on it. So I will draw an arrow downwards to indicate that there is a downward force due to gravity. Again, I'm careful to let this be my scale, but be careful of my other forces. Just because they give you a nice long string here doesn't mean that's the length of that force. When you go to draw in the next force, which I'm going to call a tension, I'm paying more attention to the detail of how long I draw this and the angle than anything else. It shouldn't be so long that it's big enough to pick the wagon up, unless that was the goal. But I think the wagon is on the ground. So I'm drawing this one so that the upward portion is not bigger than the weight of the object. Intentionally so. I'm gonna label this a tension. Some of you label it applied force, that's fine. Don't really care, but if they give you something to use on your test, you should use the variables they give you. In the absence of them, you just have to make sure you are labeling your forces clearly. What many of you missed is that it's still resting on the ground. So there should be an upwards normal force here. A bunch of you got it, that's good. But the length of this vector and this portion of the vector should be about the length of the total weight. This looks unbalanced to me, so there must be some kind of resistive force in this direction. Friction is okay. Object rolls, so rolling friction will be more complicated. We will study rolling friction. But I think these forces represent what's here. On your quiz tomorrow, you need to draw a picture that is big enough to clearly identify that you understand the nature of the forces that represent the picture that's going to be given to you, and clearly can be used to help you break your forces up into their components. If your picture doesn't have those qualities, you're not going to pass tomorrow's quiz. On a test, you'll be given a region of your test to put a free body diagram in, and it should fill the region. Does everybody understand? You'll have a box. Now, that's the free body diagram. Once done, I'm going to begin to consider what coordinate system I should use. this one's not accelerating, so priority 1 doesn't get put into focus here, but priority 2 is to try and line it up with the most number of forces possible. There are 3 forces here that are perpendicular to each other, so I think setting up a coordinate system that is aligned with them is probably the best way to go. So I'm going to have a coordinate system that's aligned like so. So it's aligned with 3 of the 4 forces, labeled positive y, positive x, negative y, negative x. What we are doing now is more than just a free body diagram. We are beginning to solve the problem. This is theta. I have to break up any off-axis components, any off-axis forces into their components. Tension is off-axis, so I'll be breaking it up into its 2 components. Components that are lined up with the coordinate system I've chosen. That's going to be tension in the x direction is going to be t cosine theta, and tension in the y direction is t sine theta. Right, opposite side and adjacent side. Any questions about those? Step 5 is to apply Newton's law, which is net force in the x direction equals 0. In the x direction, I appear to have 2 forces, t cosine theta and friction. Get the sum to be equal to 0. Net force in the y direction equals 0. In the y direction, I appear to have 3 forces. I have normal force plus t sine theta minus weight equals 0. So going back through step 1, step 2, step 3, step 4, and step 5. These are the 5 things I'm expecting of you tomorrow. Again, the point is to produce something that might be of use to you. There are uses here. For example, I could use this to figure out with what force I could pull to just lift this off the ground if I was pulling at this angle. You see, the normal force is what you call a responding force. It responds to the situation of a problem. The amount of normal force here depends on how much I pull upwards on the wagon. If I want to find out how much force is necessary to lift the wagon off the ground, I can just set the normal force to 0. Understanding that you can adjust these to figure out something else is important. The normal force is, again, what I call a responding force. There are several different kinds of responding forces, meaning they respond to the situation of the problem. We will often use the normal force and the fact that it's a responding force to look at limiting conditions of a problem. When the normal force goes to 0, that's a limiting condition. It suddenly loses contact with the ground. That's a limit on the conditions of the problem. Responding forces are forces that we will always use to manipulate the limits of a problem. Again, I said the word responding force 6 times. I've noticed 3 of you write it down. You're sending me a message. I'm not sure it's the message you want me to have, but you're sending me a message. Ready to go to example 6? Because I am. You clearly are. For example 6, I'm going to actively try and trick you. So far, I've been only 30% effective at tricking students today. I was hoping for better. So that's good. You're not being tricked. So I have an elevator with a person inside. They are 60 kilograms. The elevator is going downwards with a constant velocity. I would like you to take and figure out the free body diagram for the person. I'm only interested in the person. Some interesting choices being made. I'm interested in the person, so luckily, all of you have a downward force of weight for the person. That's good. I didn't catch anybody in this class saying that the upward force on the person was tension. That's good. Tension doesn't act on the person. A normal force does. Maybe I just didn't catch anybody, but I did in the other classes. On the other hand, they should be balanced. The fact that the elevator is going down doesn't matter. It's going down at a constant velocity, so the net force is still 0. This is still a first law problem. Now, if the elevator were accelerating downwards, that's different, but it's not. Right? Doesn't matter whether it's going up or down. These two forces are balanced if the velocity is constant. Now, a few things I want to add to this. The weight is 60 times 10, right? mg. That would be 600 kilograms meters per second squared. This is the unit of force. The unit of force is the Newton. We'll just use a capital N, but for a long time, I will write out the word Newton as to not confuse it with normal force. So people do that. So if a problem says it's 20 N's, it's 20 Newtons. But when we do abbreviate, you use a capital N out of respect because it's a proper name. Same with joule, same with watt. These are all proper names. So capital N for Newton. 10 newtons is 2.2 pounds. Pound is the English unit for force, in the same way that Newton is the unit for force in the metric system. So you tend to think of kilograms and pounds as being the same, but they are not. The English unit for mass is the stone or the slug. So, but I mean, it doesn't come up at all. But understand this is the conversion. So if you know how many pounds you weigh, you can convert to the number of newtons you weigh. Now, truthfully, it should be 9.8 newtons for every 2.2 pounds. But I'm not going to spend a lot of time with the difference. It's just not enough. All right. Take a moment now, since we've done this, and tell me about the forces acting on the elevator. Can you do a free body diagram for the elevator? So a person pushes a box up a ramp at constant velocity. The box, mass m, is moving up the ramp at a constant velocity. Can you draw a free body diagram to describe this, please? And let's go ahead and maybe try out the whole thing, right? All 5 steps, work to get yourself into a relationship. We don't have much time, but I think this is a good example for us to try and get to the end of. Several of what I'm seeing out there are going to be bad. So downward force for weight. That makes a lot of sense, right? Now, it's resting on a surface. So if you're drawing a force, a contact force from the surface, it has to be perpendicular to the surface. You don't get choices here. If it's touching a surface and you say there's a normal force, it has to be perpendicular to the surface. Be careful, be aware, but more importantly, be accurate. You have protractors and such. We're expecting accuracy here. And what I mean by that is there should be a clear and honest attempt to try and represent the direction and anything that might be perpendicular to this direction. Now, I'm pretty confident that this normal force is from the ramp. I'm not sure I've drawn the length of it to be particularly good. I think it's probably going to be a little less. So I'm going to reduce it down some, because I think there's some other things that are supporting the weight of the object. Like, I think this guy's applying a force in this direction. This would be another normal force because they're pushing on it. And if you said applied force, fine. But I'm going to say that this is the normal force from the ramp. And this could be the normal force from the person. Now, I really don't know how long to make this one. You see, there doesn't have to be friction. There's sometimes clues about whether you're supposed to be thinking about friction or not. If this is a smooth ramp, then they're suggesting to you there is no friction. That word means that there's no friction in the problem. So if they say the word smooth, they're indicating the friction is either very small or non-existent. in which case I would probably want to draw a smaller force. One that just balances the part of the weight that's down the ramp. On the other hand, if they say that the surface is rough, then they are specifically saying that there's friction. The word rough and smooth. That is it's not code. That's how they can indicate that you will have to include friction without saying the word friction. Rough and smooth. If there is a frictional force, by definition, friction is perpendicular to the normal force and is parallel to the surface. That's going to have to be this direction because the normal force that is causing the frictional force is the normal force from the ramp. Now, a lot of you began to try and break these up into components, but I saw what you were trying to do. Be thoughtful here. If I'm going to decide on a direction for my coordinate system, it's either, I can align it any way that I want, but a bunch of you must have aligned yours like this because of what I saw you doing next. I think this is a poor choice. If you align your coordinate system like this, 3 of your 4 forces are going to have to be broken up into components. This seems like the wrong way to do this. If it were me, I would follow priority number 2, which if your system is not accelerating, try and line up your coordinate system with as many forces as possible. And again, I'm trying to use colors here to help me separate what are the forces from what is the coordinate system. I'm encouraging you to do something in your notes to try and help with that. This will be the positive x direction. This will be the negative x direction. This will be the positive y direction. This will be the negative y direction. Usually the hardest part for students who are first coming to physics and having to deal with inclined plane problems, which is what this is where theta goes. You'll need to come to grips with that. Theta's here. And if you don't know why, you need to think it through. There's a good way to think about it. And the easiest way to think about it is what happens when this goes to 0? Wouldn't the weight have to point straight down? If this one was the one that was going to 0, the weight would not be pointing straight down. So be cognizant. Find a way to convince yourself of where theta goes in an inclined plane problem. Either way, once you've gotten to this point, your job is prescriptive. Break the weight up into its components. I'm going to have weight sine theta and weight cosine theta. Breaking it up into its components. Net force in the x direction equals 0. Looks to be like that's going to be the normal force from the person minus the weight sine theta minus friction equals 0. These are all of the forces that are aligned with the x direction. Net force in the y direction has to equal 0. I've got the normal force from the ramp minus weight cosine theta has to equal 0. I've generated 2 relationships that could be used to help me figure things out about this system. Generally, we're interested in the relationship between friction and the normal force. They're related. Anyways, we're interested in the relationship between the normal force and the frictional force. This is what I need you guys to do tomorrow. And it's got to be perfect, right? So I'm going to be very clear. It's right or wrong. You either get 100% or you don't. You're not going to be partial credit on this. Does everybody understand? Because you understand that if you draw this wrong, everything from there on out is going to be incorrect, right? There's no way to get to a solution. This part has to be done perfect. You get your notes tomorrow. I would encourage you to make sure that they work, because if you were unable to do these with your notes in hand and people around you helping you, what does that say about tomorrow? All right? At your table, there'll be 3 or 4 different situations. You'll draw them like cards, and that's going to be the one you have to do.